Hi, this is a quick recap for anyone who missed or wants to revisit the content of September 15th, Tuesday, September 15th, week 3 for EG325. So we talked about free body diagrams, and you can see this example in the text where there's a gear reduction box with two shafts, two gears, and plates holding the shafts in place. And then this is decomposed into 3 free body diagrams. And mostly what I emphasized here is remembering that when you take elements apart, the points of contact have equal and opposite forces. So at A here, you have the reactions at A in the Y and Z directions, and then on the shaft, the reactions in the Y and Z directions at A are in the opposite direction. Similarly on the gears, right? Force F is equal and opposite on gear 1 as it is to gear 2. And so as we put free body diagrams together, this is an example I did in class where we took apart link AB and OAC and drew the free body diagrams and identified how we would find reaction forces. And so at this point, if you want to pause, make some notes, draw your free body diagram, and then join me. We'll take a look at the free body diagram and solution that I showed in class as an example. Okay, so this is what we put together in class. So you can see element OAC is drawn here, and you have AB here. Everything's separated vertically and horizontally by the same length. And I've done everything here in terms of variables because ultimately this is generically true. It doesn't require us to apply numbers. So in red here you can see the force at C was applied and provided. At O we can have an X and a Y reaction force. At A we have an X and a Y reaction force. And I represented my 2 reaction forces, or my 4 reaction forces at my 2 points of interest here in their positive directions. That way if they come out negative, I understand intuitively that those are negative. When I'm looking at AB, I can see that A has equal and opposite direction for reactions, and B, I drew those positive. Now, you might also identify that AB is a 2-force member, and so if you draw a line between A and B, that is the reaction force at A and B. And so it depends on how you want to represent and solve this for how you represent your forces. Now, another point to notice is as I'm using equilibrium to solve for my reaction forces, I want to note which free body diagram I'm referencing. And so free body OAC has reactions at O and A in the X directions, reactions at O and A in the Y, as well as the applied force, and then I can solve the moments about point O. AB, I've noted here that it is a 2-force member, so I know that RA and RB are equal and applied in opposite directions, but I can also just break it into its components. Ultimately, this is 6 equations, 6 unknowns, and the system is solved. So then we took a look at shear and bending diagrams, and we reviewed the idea of taking a loading. This here is shown as a fixed beam, most likely a cantilever fix here, with an applied moment at D and a distributed loading from B to C. And so my first step here would be to identify R1, the reaction at A, and M1, the moment at A. And that's going to provide for me my initial shear force and my initial bending moment. And then I notice from A to B there is no external loading on the beam. And so the shear force stays constant. So we see this step function from A to B where it steps up at A and stays constant at B until B. From B to C, we have a constant loading of 20 pounds per inch, which on my shear force diagram, I have a ramp. And so that's my internal shear force ramps down to 0. and there are no forces from C to D, and so my shear is at 0, which is what it should be. For an equilibrium scenario to apply, I need to end up back at 0 for both my shear and my bending diagrams. So for bending, I base this off of my shear diagram. So I step down to whatever M1 is, and then if shear is constant, my moment diagram should be linear. So from A to B, I have a straight line with a slope equal to the constant shear force. At B, this changes from a linear shear diagram to a parabolic or quadratic, very specifically, function that from B to C gets to the quantity of D's applied moment, because from C to D my moment stays constant and my bending moment then steps down by the applied moment D to 0. And so that is the idea of how we apply a shear, how we apply loadings to develop our shear and bending diagrams. So now we have another example, and again I'll have you pause and think about how you would approach this problem with an applied load, concentrated load at A, a distributed load from B to C, and it's a cantilever beam fixed at O. So pause here, take a moment to consider how you would complete this problem, and then we'll look at what I developed in class. Okay, so in class, we first started with our beam. So beam has a reaction force in the y direction. It could support an x direction reaction, but there is no other loading in the x direction, so I did not draw that on my diagram. And I represented M1 here. So we note that the distributed force can be represented as a concentrated force that is equal to the area of this distribution, or 40 pounds per inch times 6 inches over which it is applied. So I know my quantity, and a concentrated load applies through the centroid of the area of the distributed load. This is rectangular, and so it acts through the center, and so it's 3 inches from B and from C. So I can then, obviously the forces in the x are not interesting because there are none. In the y direction, I have my reaction force and my applied forces, and my moments about O here are due to the resulting supporting moment, the reaction moment at O, and then my moments due to the applied forces. So I can solve for R1 and M1. There's only one unknown in each equation. And so R1 then is a known quantity. And if we look at our shear diagram first, we go from 0 up to R1 in an immediate step, and there's nothing between O and A, so it stays constant. It then steps down by 500 pounds, and again stays constant because there are no applied loadings. From B to C, we see a linear ramp with a slope of -40 and get back to 0 at C. For our bending moment, we step down to M1, and then because our shear is constant and non-zero, we have a linear change in moment of slope R1. And then the slope changes, and the slope here would be 240, and so my slope changes. And at B, my bending moment begins to be a downward-facing parabola with decreasing slope to 0. And so that is the shear and bending diagrams for the example problem. I'm going to pause here and do Moore's circle separately. That is the next thing that we covered on Tuesday, September 15th.